The next one is a bit more involved. It is something called, it's an example of a neural network, right? For those of you who have done some reading on the background of image processing, you would know that AlexNet in 2012 was sort of the neural network that triggered the whole deep learning craze, right? Essentially what it showed was that by using a deep network, one with many layers, you could get performance that completely outclassed any other approaches that were used for image processing, to the extent that within a year or so, all the traditional methods that were used for image recognition had basically been dropped and people had switched over to neural network based systems. Okay. AlexNet is a complex structure, but it's nothing compared to what exists nowadays, right? The number of layers, the number of different types of layers are like huge. By comparison, this is actually a very simple network. Okay. This structure you can see over here already looks very complex. All that it's saying basically is something like this. You have an image, which is actually something like a 224 pixels by 224 pixels by 3 colors. Okay, and what you do is implement certain kinds of convolution operations on this. Okay, a convolution operation can be thought of as, you basically take a small square and impose it on top of this and do a point by point multiplication. Okay, so this unit over here could be something like 11 cross 11 cross 3. Okay, so 11 cross 11 cross 3 block of coefficients. Just put it onto your image, onto one part of your image, do a point by point dot product, you get one number as the output. Okay, take that number to your next stage. Okay, so that is one of the elements in the next stage of your computation. Like that, you create a whole set of different such operations, and in fact you say, I'm not just going to stop there, I'm going to go further and create a further block of those. Okay, so this could be something like 96 different elements. Okay, so that essentially it was what it says over here. The 224 cross 224 cross 3, the input image, is put through 96 kernels of 11 cross 11 cross 3 with a stride of 4, right? I'm not going to go into the details of this because it will just take too much time. We'll get to this later and actually go through the calculations at one point. But roughly what you can see is, in order to compute one kernel, right, out here, you can see that it involves 11 into 11 into 3 multiply adds. That is to compute one dot product, one output over here. The number of outputs is going to be that into, in this case, 55 into 55 because you are doing a stride of 4, etc., and into 96 because there are 96 such outputs. Okay. The bottom line is, the kind of number of computations that you are going to be dealing with over here, right, the number of weights just in this first layer is approximately 35,000 or so, right. The number of computations is a few million, right. I don't remember the exact number, I think it's somewhere around 10 million or thereabouts. Okay, I'm probably, this number is not accurate, but you can estimate it. It's basically 11 into 11 into 3 into 96 into 55 into 55, right. You do the computation, you will come up with a number over here. Okay, but that's just the first layer. After that, you have 4 more such convolutional layers, and then you have 3 so-called fully connected layers. A fully connected layer is literally, as the name suggests, you have n inputs, m outputs, n into m connections. Okay, so the number of connections is large, number of multiply adds is also correspondingly large. Okay, once again, bottom line that comes out over here is the total number of computations. Layer 1 is approximately around 10 million, layer 2 is approximately somewhere around 100 million, L3, L4, L5, all are in the region of 100 to 200 to 50 million or so, right? And in some cases, because you need to do additional computations before you can reduce it, in fact it's more than 200, it probably goes to around 800 900 million, okay, per layer. So when you add all of this together, we can see that the number that you come up with is somewhere around 1500 million multiply accumulate operations, and at least the original AlexNet was just implemented using floating point computation, because they were not very concerned about hardware implementation, they just wanted to demonstrate that the recognition worked, okay. So this basically is the number of floating point operations. Another way of putting it is around 1.5 giga flops, okay. Note this is just operations, not operations per second, because I don't care about speed yet, okay. But you can see that, you know, the kind of computation that we are talking about over here, the FFTs, we were saying, okay, I needed 20 gigamax per second. Here I don't care about per second, I'm just telling you this is the number of operations I need to do in order to recognize one image. Now what's the best speed at which you can do it, right? So this is an example of an application where I do not have real-time constraints. I am not concerned with this is the speed at which you need to recognize images. You might at some point if you are actually putting it into a real-time video or something, but let's say that you are just uploading data onto Google and Google is just using this to recognize faces. They are not doing it in real time, right? They just do it as fast as they can, possibly faster than real time, okay. So what this means is the number of parameters, by the way, is also something that you can estimate. It turns out there are a few million, around like 10 million parameters or so that need to be stored in order to implement all of AlexNet. Those parameters that I'm talking about are basically the weights on each of those layers. The number of M flops we saw is somewhere around 1500 to 2000, somewhere in that range. Now we saw this number around, let's say 2000, okay, 2 gigaflops, okay. So that's the estimate that we have got right now from our computation. There's one website over here where this person has basically gone and done benchmarking of networks. This is a couple of years old, so it's basically they have data from 2016 and have estimated that there is one particular GPU, the NVIDIA Pascal Titan X, which is pretty much the top of the line as of that date, which was capable of a peak performance of 10 teraflops, okay. And the time that he observed for running one instance of AlexNet, basically recognizing per image, was approximately around 5 milliseconds or so, alright. So let's do the math. 10 teraflops peak into 5 milliseconds is 50 gigaflops, 50 billion floating point operations. Where did the remaining 48 go? Okay, because what we are saying is one image on AlexNet should have taken us 2 gigaflops. The processor is capable of handling 10 teraflops. It took 5 milliseconds. Within 5 milliseconds, the peak performance could have been 50 gigaflops, 50 billion floating point operations. But we only recognized one image, which is 2 billion floating point operations. Okay, what happened to the rest? Okay, and this is one of the crucial things that we'll have to understand as we move forward. The answer, if you think about it, is fairly simple. This 10 is a peak number. Ideal situation, all numbers sitting in registers, all you are trying to do is load them into your ALU, multiply and write the result back into a register. If you keep on doing that, yes, you will get 10 teraflops of throughput. But AlexNet is not as simple as that. I need to read weights, I need to read data, I need to do some computation, I need to store it back into memory. Those memory accesses are not completely regular, they are highly regular but not absolutely regular. Therefore, there will be some latencies involved over there. But you can see the impact. Effectively, what I have got is I have had a 25x reduction in efficiency. From what could have been 50 gigaflops, I have dropped to 2 gigaflops of throughput effectively.